As you can see, when you have used this read.csv and the data has been ingested into R and you have allocated the data to data, not a good idea to write the name as data because it's confusing, but still it has been used. Okay. Now, when you do a head data 10, it is showing you the first 10 observations. So selected is the actual Y or the dependent variable which we are wanting to do the modeling on. You have stats, rank, percentage, and you can see zeros and ones in selected. The one is the event which you want to model on. That is the rare event of being selected for some course, right? So you can do a two-way contingency table of the categorical outcome and predictors. So you can use cross tabs, X tabs, or you can use the table function also. We have already seen this before. So when you're using X tabs, you can just use the tilde sign selected plus rank and the data is equal to data, and you'll get this grid. So you understand that when a person, right, if you can relate the 1, 2, 3, 4. So higher number of people have been selected when the grade of the college. Now again, you need to take a proportion out of this, right? So out of 9 by 10. So if the rank of the college is 1, the number of people who are getting selected for the course is equivalent, almost equivalent to the number of people who are not getting selected, right? But if the rank of the college is say 4, the number of people who are getting selected for the course is almost, you can say, I would say 5% of the overall data, roughly, rough computation, because 19 to 1, right? That means 19 people have not been selected and 1 person has been selected. So that shows a spectrum in the data, right? So basically rank is affecting, but not completely. It's affecting your chances of being selected, but not very high. Yeah, but there is some difference. So if the rank of the college is 1 or the institute is 1, it doesn't say that you are going to be selected for sure. But yes, if the rank of your college is 4, there is a surety that you are not going to be selected. So you need to look at the data from that perspective also, right? So the formulation when you're going to use a logistic regression model is GLM, which stands for Generalized Linear Model. The first parameter is the formula. So similar to a linear regression model, y tilde x1, x2, x3, comma. Now here is the additional part. Family is about, you have to specify this parameter. Family is equal to binomial logit. So that is the link function which you have seen theoretically, and you have to supply that to the algorithm for it to understand that you're doing a logistic regression model. Because a GLM can do a probit model also, and there are other link functions also like exponent and all those things which could be used. So if you want to specifically use logistic regression, you have to specify that. Then you have to pass the data, and the rest of the things are not compulsory, weights and subset. It depends upon whether you want to do a training and a testing data set, and accordingly you will use that. So here are a list of the link functions which traditionally people use. So if the family is Gaussian, then the link function is identity. So you would not be using this. You would be using the logit link function. So what you can see in this second line, binomial, the variance is binomial. That means you have only two variability, like the class is only two variables. Then you are using logit, probit, or C log log. Out of this, logit and probit gives you similar results. The C log log is for different notions wherein data has very low variance. The logit is more dominantly used. The probit is not that often used, right? And it also assumes an assumption that you already know the probability distribution, which we usually don't know. The rest of them, like the Poisson, is depending upon what kind of data you're working. So if it is about failure data, you might use the Poisson link function. So for that you have log, identity, or square root. If you want to work on some data which has a gamma distribution, then you'll use the link function as inverse, identity, or log. If you have an inverse Gaussian, that is inverse of normal distribution, then you will use 1 minus sigma square. And if it is a quasi, that means it's a user defined function, then you will have to create your own user defined function. Model, allocation, GLM, we are going to repeat all these things in a data set which I have access to. Model, allocation, GLM, selected is the variable, tilde stats plus percent, and plus as dot factor rank. Now why is this as dot factor done over here is because rank, although is shown as a numerical variable, it actually has a meaning of a categorical class data. So that is why you have to make sure that that is taken as a factor, right? And the family is binomial. Actually you should pass family is equal to binomial, inside bracket you should pass logit. That's how it is written. Now once you do this, this model will be allocated to this whole equation will be written in the model typecast, and then you can do a summary and you can get the output, right? Okay, so we'll go ahead and see what's next. So you will see an output like this, right? Not similar to what you had seen. Now most of the things will be common, like the coefficients and all those things. If you do a summary of model, you will get exactly the same kind of an output. The only difference will be that at the bottom you won't be getting a regression table, you won't be getting an R square value, you won't be getting an adjusted R square value. Instead you will be getting something like a null deviance, residual deviance, and the AIC. Now the null deviance is nothing but what would come as an error or a or something like a gap, right, or something like a residual if your model doesn't have any variable in it, right? For example, say I say selected is the y, but I am not passing any x, right? In that case, that is null deviance. It's standing at 121. When you say residual deviance, it means if you have a model which has one variable or some other multiple variables, what is the error which is creating? Now obviously this has to be less than the null model, right? So in this case it is 121 versus 100. That means the error is reducing, and you expect this gap to be higher and the residual deviance to go lower and lower. The AIC also, if you keep on adding variables in your model, AIC is a comparative figure. So if you just run the whole model, you cannot make out any difference. So if you add one variable at one time and then see the effect on the model, the AIC should typically go down, right? That's an indication that your model is improving in performance, right? And also if you want to change the ranks, right? So for example, if you want to make rank 1 as the base variable or rank 4 as the base variable, you can use the relevel function to change the base category. But if you do that also, it doesn't have any impact on your model. It remains as it is. It is just for business purpose that sometimes you might want a specific level to be shown as a base and interpretation related on that. That's where you use it. So again, a summary of the same. So again, you see the same kind of output. The regression table is there, but as you go down, you're not seeing the R square, the adjusted R square, and all those things, the F value. Instead, you're seeing the AIC, the null deviance, and the residual deviance. You can see the null deviance has 100 degrees of freedom. So basis data is showing everything. Now, if you are looking at the whole model, that is n minus k plus 1. So the degrees of freedom. So say 100. Right, 100 minus how many variables are there in the equation? So you can see 1, 2, 3, 4, 5, right? So 101 minus 5 plus 1, 6. That's how you compute the degrees of freedom. So AIC is 112. Now this doesn't make sense. You can understand the implication of AIC when you use one variable at one time. Also, one difference is that in this output you are not actually creating anything called as dummy variables, and that is why R by default is creating the dummy variables as rank 2, rank 3, rank 4. But supposedly in this case, as you can see, rank 4 is significant, right? The p value is less than 0.05. That's good for you, but you're not interested in the other factors. But because it's part of the same column, you cannot isolate the effect of 4 from the remaining, right? So for that you might need to do something called as dummy variable creation, which eventually we'll be doing in some future sessions. So the logistic regression example which you have seen over here, and from the interpretation perspective, if you have to understand, it's the null deviance versus the residual deviance. You expect a higher difference between the null and the residual deviance. The null is going to be higher, the residual deviance has to be lower than the null, and as you keep on adding variables or removing variables from your model to improve the performance, you expect the residual deviance to be comparatively smaller and go on a reducing scale. The AIC is also the same thing. It is also going to direct in the same direction. The next part of the output shows the coefficient, the standard errors, the Z statistics, sometimes called as Wald Z statistics, and the associated p value. So what you're seeing in the regression table as the Z is nothing but the Wald Z statistic, and it is observed for every variable. In your linear regression model, you are referring to this very same thing as a t statistic. In this case, it is replaced by the Z statistic, right? And the remaining thing remain as it is. So stats is a statistically significant variable, and so is rank 4. So the logistic regression coefficient gives the change in log odds of an outcome for 1 unit increase in the predictor or predicted variable. Now you cannot relate it in the same terms. Why? Because you have done the transformation. You have created odds, the odds ratio, the log odds. So obviously when you're giving the inference, it has to be in that term only, right? So when you say that if the rank of a person is 4, that means if I say value 1 over there, that means if a person is from an institute which has 4th rank, the log odd of y, which is being selected, is this value. That's the interpretation. That's how you have to see it. Right, so just a little bit of brief around the odds ratio. So you can, if you want to avoid the log expression, right, but still express to business this odds ratio, what you can do is, you have got the coefficients, you need to do an exponential of the coefficient, so that if you do an exponential, the log is removed, right? So then you can express the same as an odds ratio. In that case, a 1 unit increase in stats, which is your variable over here, the odds of being selected for an analytics job versus not being selected, which is the base, increases by a factor of 1.0401. That's how we'll infer it. The function that we use to extract results from the fit, so it's the same one which you use for linear regression, residual, model, fitted dot values for model, predict model. These continue over here also. You can get the confidence interval also for the 97.5 and 2.5. Why? Because the base is 0.05 as the alpha value, right? So obviously the confidence level is 95. So that is why from 2.5 to 97.5, 2.5 on the left hand side and 2.5 on the right hand side. That's why you're getting that confidence limit, right? So if you want to do the wall test independently, we can test for the overall effect of rank using the wall test function. So wall.test b is equal to coefficient of model and pass the sigma as the weak covariance of model, terms is 4:6, and that gives you the wall test. So you're getting chi-square of 0.11, right? So what you can do, what you can understand from this is that the test statistic of 6.1, right? The chi-square is 6.1, which is high, with 3 degrees of freedom is associated with a p-value of 0.11, indicating that the overall effect of rank is not statistically significant. Had this p-value been less than 0.05, you could have made a statement that this is statistically significant, right? So that's the outcome when you do the wall test. So the predicted probability, right? So now when you see an outcome, when you're doing linear regression, the predictions were actually point predictions. But when you're doing predictions in logistic regression, you're not getting the actual class. What you're getting as an output is the probability of the event happening. So this could range from 0.001 to 0.999, indicating higher the probability of the event, higher is the possibility of that event happening. That's how you will see it. Right? The deviance, that is the goodness of fit test, the residual deviance, lower the residual deviance, the better it is for us. Larger the value of deviance versus the fit test, right? So the deviance is similar to the sum of squared errors in a linear regression and accounts for the unexplained variance in the dependent variable, right? And the wall test is basically used to check the significance of the individual explanatory variable, and something similar to the t, wherein we were saying b1 divided by standard error of b1. In this case it is w is equal to beta 1 estimated divided by standard error of beta 1 cap. W follows a normal distribution, right? And then again, when we do this, right, to statistically test the overall model, so wall test talks about basically individual variable significance test, but if I have to talk about the overall model significance test, I will have to chop the data into 10 equal parts, maybe basis arranging the probability values, right? And then as normal, I would expect that the bucket of data wherein the probability value is higher, I expect a higher degree of the event happening. So if default is happening for all those data points which are coming in the bucket wherein the probability is around 0.95 mean value, I expect more people to default. Wherein the probability of the default as per my modeling is less, say around 0.05 mean value, I expect less number of people to default. So I expect this variation to be visible. So it's like I'm bifurcating, say for example, parallelly, if I am saying there is a class wherein I am bifurcating 10 students into 5 group, and one group is exposed to tuition and one group is not going to tuition. What I expect is that the guys who are going to tuition and the guys who are not going to tuition show a different behavior. If both of them show a similar behavior in terms of outcomes and marks, that means the treatment or the stimulus which I am giving is not effective. That is what I am trying to test over here with the Hosmer-Lemeshow goodness of fit test, right? So basically testing the observed minus expected divided by the expected, right? And it's done in bulk. So if the Hosmer-Lemeshow goodness of fit test statistic is 0.05 or less than that, we reject the null hypothesis that there is no difference between the observed and the predicted values of the dependent. If that happens, the alternate is selected, which says that there is variability in the behavior of each bucket of data, and that is what we expect, right? So that expresses that our model is statistically significant.